Okay, here we go with a question all about gas in a container. We're asking about what happens to the density and the pressure when we hold the same number of more massive molecules at the same temperature. Okay, I'm assuming you've had a chance to have a go at that one. Here's an attempt to explain the answer. So we're looking here at density and pressure. I tend to just look at these things and take one by one, and we'll go with density first. Hopefully that's a more straightforward one. What we've got there is the fact that density is mass over volume. Okay, now the mass is just the number of particles, same number, and multiplied by the mass and divided by the volume. Now we're assuming the number and the volume are the same, so really we're interested in m, the mass of the molecule itself. Well, as m goes up, density is going to go up, so we're going to get rid of A and B initially. The pressure. Pressure is a slightly different one to think about, and for this one I was thinking sort of along this line about the idea of pressure going with 1 over 3 nmc squared. This comes from our conservation of momentum, etc. It's the idea of the particle in a box. Okay, now key to this idea is c squared. Okay, and it can be a little bit confusing for this. So actually I tried a different equation here, which is just the simple one, PV equal to nRT. And at that point I actually realized this question is very, very simple. If we have the same volume, we have the same temperature, the same number of moles, i.e. the same number of particles, and obviously the same R, the pressure is going to be the same. Okay, you can see there P is equal to nRT over V, everything else is a constant, and therefore we get the same pressure. Now the reason that, as I say, it gets a little bit confusing, this c squared, we've got a kind of double change with the mass, c squared is going to go down, but in effect those two effects are going to cancel each other out. Far better to use our PV equal to nRT here to get the same pressure.